Hello friends. Think about a pendulum swinging back and forth, or a sound wave traveling through air. Both of these systems follow a sine curve. But here is the real question. At any single instant along that curve, how fast is the value actually changing? That is exactly what a derivative tells us. And when our functions involve sine, cosine, and their relatives, we need a special set of rules to find those instantaneous rates of change. In this video, we are going to build those rules from the ground up, understand where they come from, and learn how to apply them confidently. Let us start by making sure the foundation is solid. Before we derive anything, let us revisit two tools we will lean on heavily. The derivative of a function f at x is defined as the limit, as h approaches 0, of the quantity f of x plus h, minus f of x, all divided by h. That is the instantaneous rate of change, captured precisely. Now, two specific trig limits make everything in this topic work. First, the limit as x approaches 0, of sine x divided by x equals 1. Second, the limit as x approaches 0, of cosine x minus 1, all divided by x, equals 0. These are not obvious facts, but they are provable from geometry. Every trig derivative rule we build today traces directly back to these two limits. Keep them in mind as we move forward. Now let us state the 6 rules you need to know. The derivative of sine x is cosine x. We can prove this directly from the limit definition, and those two trig limits do all the heavy lifting. The derivative of cosine x is negative sine x. Notice the sign flip. For the remaining 4, each follows from the quotient rule applied to sine and cosine. The derivative of tangent x is secant squared x. The derivative of cotangent x is negative cosecant squared x. The derivative of secant x is secant x times tangent x. And the derivative of cosecant x is negative cosecant x times cotangent x. Here is the pattern worth noticing. Every cofunction rule, cosine, cotangent, cosecant, picks up a negative sign. That symmetry is not a coincidence, and it is a powerful memory aid. Next, we extend these rules to composite functions. The 6 rules we just learned apply directly when the argument is simply x. But what if it is something more complex, like 3x squared, or e to the x? That is where the chain rule comes in. The chain rule says, differentiate the outer function, leave the inner function alone, then multiply by the derivative of the inner function. Take y equals sine of 3x squared. The outer function is sine, so differentiating it gives cosine of 3x squared. The inner function is 3x squared, whose derivative is 6x. Multiply them together, and you get cosine of 3x squared times 6x. For y equals cosine of e to the x, the outer derivative gives negative sine of e to the x, and the inner derivative is e to the x. So the answer is negative sine of e to the x times e to the x. One clean pattern, applied twice. Next, we will see this same pattern, combined with the product rule and implicit differentiation. Let us put the rules together with two mixed problems. First, a product rule case. For y equals x squared times sine x, we treat x squared as one factor and sine x as the other. The product rule gives us 2x times sine x, plus x squared times cosine x. We use the trig derivative rule on sine x, and the power rule on x squared, simultaneously. Now for implicit differentiation. Suppose sine of y equals x. Differentiating both sides with respect to x, the left side requires the chain rule on sine of y. That gives cosine of y times dy divided by dx. The right side differentiates to 1. Solving, dy divided by dx equals 1 divided by cosine of y. In both problems, trig derivative rules slotted in naturally alongside the other techniques. Next, we lock in the patterns so they are easy to remember. Let us bring it all together. We started with 2 foundational trig limits, used them to derive the 6 core rules, extended them with the chain rule, and combined them with the product rule and implicit differentiation. The single most useful pattern to memorize is the cofunction sine rule. The derivatives of cosine, cotangent, and cosecant all carry a negative sign. Their counterparts, sine, tangent, and secant, do not. If you can remember that contrast, you have already cut your memorization in half. A helpful mnemonic is to list the functions in pairs and note which partner flips the sign. From there, practice is everything. Work through a few problems applying one rule at a time, and the patterns will become second nature very quickly. Thanks for watching, friends, and we will see you in the next video.